All right, finally, after you could say a delay, we're finally getting started here, and this is approximately where we had left off with last time. And just remind me at the end of the hour, I do believe there are some papers that I do need to collect. With last week being a busy week, one thing led to another, and it just totally slipped my mind, which sometimes wonder. You saw me earlier hitting the old noggin, trying to wake the hamster up because he's taking a nap. He must have fell off the wheel. I don't know. But the language that we use here, we really got to be specific, okay? Oops, wrong button. When we use this, we want to talk about the asymmetric reagent, which could be water, it could be hydrogen iodide, hydrogen bromide, where you have a hydrogen and a halogen, as opposed to the symmetrical type, which is chlorine, bromine, iodine, where you have a diatomic molecule that would be your symmetrical type. Okay, moving forward, this is just a review from that of general chemistry combustion. We know that anytime you have a spark and enough oxygen with an alkene and alkane, any one of those, even an alkyne, they will burn, and then you will have the process of combustion take place. No surprise there. Should you have to write an equation for an alkene, those get to be a little more tricky because it's just the reverse of what you would think from what you had learned in general chemistry. And I'm going to ask just to see once what you do remember from general chemistry. Okay, so you have an alkane, okay? So C3H8 plus oxygen, in other words, that's propane, plus oxygen gives you carbon dioxide and water. Or butane, C4H10 plus oxygen, still gives you carbon dioxide and that of water. But which one would you rather balance? The propane, the C3 compound, or the butane C4 compound? Propane? You are, well, you can do the butane, but what we learned last year, the C3 or propane is much easier to balance. Why is that? Because it's an odd number. The reverse happens when you're dealing with alkenes. You'd rather do C3H6 as opposed to you'd rather do C4H8 as opposed to C3H6, because then if it's an odd number, then you have to double that. Okay. So we just spend a little bit of time with that on the alkynes, and then we're going to start talking about the, oh, wait a minute. Okay. 2 slides on the alkynes. Would have been much easier if this technology would have cooperated before. But, well, there again, we can only control what happens here. We can only react and control with certain aspects. The technology, we can't control that. And oddly enough, I thought about this over the weekend when I was reading a segment out of Reader's Digest. When it comes to your possibly buying flowers, you're much better off not getting them from a place like Hy-Vee or a store-bought floral, what I want to say, shop to that effect, because they just won't last as long, because according to the article, some of these plants will let out ethene gas, okay? In other words, that would be 2 carbons, of course. And if that is the case, how many hydrogens would that be? If you can visualize that in your head. C2H what? Okay, so if it's ethene, remember that means it's a alkene. There's a double bond. You only have 2 carbons. So there's 2 bonds between the 2 carbons, and it only wants 4. So that means each carbon can only hold how many more hydrogens? Okay, and sometimes it's hard to visualize that. No problem, okay? And we'll get to these in just a moment. See, we look smarter when we see these things up on the board. You say, wow, look at what them organic students are doing. They're really smarter. I don't know, just sounds good. So ethene, so you got your double bonded carbon. So that means each one of those can hold how many more hydrogens? Yeah. Whether you put top and bottom or top on the side, doesn't make any difference. So some of these flowers, plants will let this gas leak out, and that causes them to, according to the article, decompose much faster. Now, why that is, that I don't know. But I thought that was kind of neat because that's something that, if I can remember, I should bring that here, because only a select few people that would read that article, well, what's ethene? Well, it's just a 2-carbon compound with 4 hydrogens total. Okay. So there's our formula. Remember, when we're saying Cn2n minus 2, okay, I should have left that up here. So when we're dealing with an alkene, as we had, it's whatever you're putting in for your number of carbons, okay, N, H, 2N, okay. So 2 goes in for that N, there's 1, 2. So how many hydrogens would that have? Well, okay, so 2 times the number that you had in here. So that being said, there is your 4 then, okay? Because again, you put N in for there, that was 2. 2 times 2 gives you 4. Alkynes on the other hand is telling you that yes, you have that triple bond in there. Okay, and what did that say? Cn2n minus 2. So there again, you're putting 2 in for n. So 2n minus 2, in other words, 2 times 2 gives you 4, and you subtract them 4, and that gives you 2. And there's 1 and 2. So that's where those formulas are actually coming from. Okay. And then I wanted to make sure that we at least just slightly introduce the aromatic compounds, which means they're all associated with the molecule benzene. Now, for some of you, when we're talking about reactions with other reagents to give complex products, that means you're probably going to possibly be taking an organic class in college, not one that's mixed with the biochemistry process where I believe nursing students would take that course, as well as dental hygienists is to the best of my knowledge. But here, if you're getting into this depth, that means you're just taking an organic class on its own, which you would probably be taking if that's what you're studying upon your next step. And I think I asked this before. Do we like drawing? The power is still good. Yep, it is. Because that's what happens when we start talking about aromatic compounds. With everything that we've talked about so far, all aliphatic compounds, your alkanes, your alkenes, and then your alkynes, and then could be some sort of alcohol. That is also an aliphatic compound. It just means that is a type of branched chain compound or a straight chain. Those are aliphatic compounds. Then the last thing that we're going to do today is I want to show you how it is we go about naming just draw those compounds that we see up, whether it's on your sheet there or your notebook. Just draw those aromatic compounds, because that's how we're going to start naming those, possibly starting tomorrow. We had a late start today due to some of the technology issues in here, but regardless, we will continue to move forward with that. So what I mean by this, okay, we don't need this anymore. And X's are just variables, okay? So put this 6-carbon-sided figure with a circle in the middle, and what that means is this. It's just a more handy way of writing. Rather than writing benzene like this, where you have the alternating double bonds, when you put that circle in there, it's just understood that that is benzene. You don't always have to draw them lines in there. So you do this, that means them alternating double bonds. And we'll tell you what the P stands for, the O stands for, and the meta. M actually stands for meta signature, ortho designation, and para designation. But we'll get to that at another time. Okay, so we will catch up to you next time.